K8BYP's video on the myth of matching 6JB6 final tubes in the Drake TR3's 4s and twins by measuring idle current. Here is a letter to a tube supplier with some pontifical statements of not that interested in dynamic matching, mainly equal currents at fixed bias level. My, that sounds sophisticated. And it's completely backwards. All this carefully taken data, screen 260, plate 650, yada yada yada, and all these carefully taken measurements, plate current 30, 21 mils, 25 mils, 75 mils, G sub M transconductance, grid current, okay. Grid currents are irrelevant in these tubes. These are receive tubes. This is a standard operating procedure for supposedly finding tubes that are matched within 10%. Because if they're not matched, they won't work correctly in these Drake Bs. That is absolutely false. That evidences no knowledge of circuit analysis and no knowledge of how tubes operate. So this video will explain the correct theories, circuit analysis, and the ways for selecting these tubes. What this does is confuses the need for neutralizing the tubes. And there's a warning stamped on the RF tune capacitor compartment on the TR3 using, I think it was Sylvania tubes. If other tubes are used, there'll be a need for realignment. That's because the Miller capacitance is different. That has nothing to do with tube gain. The problem here is that this testing is done at idle. See, what fixed bias level means is adjusting the control on the power supply for the TR3 or 4. So the idle current is 100 mils. Right here, that's the idle in key now. That's a little bit low on this one. I need to turn it up. But that means each tube is drawing about 33 mils. That's idle. That is not operating current. That is idle. This statement of not interested in dynamic matching is not only wrong but completely backwards. Tubes operate under dynamic conditions. That's what they do. They do not operate at fixed bias except to make a little bit of heat and to heat the plates up so it's not such a sudden thermal shock if they're suddenly put into service. The problem here, as shown on the JB6 plate curves, this is a plate curve for the 6JB6. Plate curves plural. And firstly notice that the factory plate curves for this tube are not sufficient for operation in these finals because it only goes to 300 volts. These tubes operate upwards of 700. So these curves are sufficient for low voltage operation. But in television service where these came from, they operated at 600 or 700 volts. But in general, screwy things happen in vacuum tubes when the current gets too low. See the difference in the saturation knee, where the tube is very nonlinear here versus low current here. We do not operate tubes in this region or in this region because they can become highly nonlinear. The goal here is to operate, as somewhat incorrectly termed, in linear operation by swinging across these more or less linear lines. And here's an example of that as I'm setting up the bias for a homebrew CW transmitter using this JB6 tube. Here's the operating line that gives a plate swing from 275 down to 75, and that traverses most of these linear regions. We avoid this area like the plague because it's highly distorted. And down in here, at these low current levels, is where these fake tests are being done for supposedly matching tubes. That's bad because a tube characteristics can be unpredictable at such low current levels. And these kind of differences in plate current are what I would expect from different tubes. They're not being operated in the linear operating region. They're being operated nearly at cutoff. And transistors do a similar thing. They get flaky at near cutoff. And that is why, especially in audio applications with push-pull amplifiers, we avoid like the plague the crossover region because it's highly distorted. What must be done with these, if we want to test the tube performance, the tube must be tested in the region in which it operates. Up in here, we need to give it a few hundred volts plate and give it 100 mils of current and get over here where it's linear. That is a valid test for a tube or a transistor. The curves for transistors look very similar, just different voltages and currents. That is a valid test. Now, to the myth that the tubes must be matched within some number of percent, and the number of percent is always fabricated. And here's the letter to the tube supplier. But this tube expert wants tubes under these conditions and has absolutely no idea what he's talking about. The reason this is irrelevant is not obvious. It's found in the circuit analysis. And this is the kind of stuff I had to do for the second-class commercial phone license back in the 70s. I had to do circuit analysis right there in front of the FCC examiner. None of this softball ham radio question. But prove to the examiner you can do circuit calculations. And by the way, nearly failed the test. So did 3/4 of the class failed it. I barely squeaked it. The reason this is irrelevant is that, as we see on the schematic, these tubes are in parallel. Common plate connection, common cathode connection. In circuit analysis of tubes, here's a triode. Let's just assume for a minute that, excuse the cough, assume for a minute that the tube is a triode. The JB6 isn't, but the other elements are irrelevant. The basic engineering analysis for a tube is that the tube is a voltage source on the grid and a current source in the plate, and that leads to the term transconductance. G sub m equals lowercase I sub b over lowercase v sub g. That means AC properties of the plate current, sub b is plate, sub g is grid. The ratio of plate current increment to grid voltage increment. I sub b is plate current increment, v sub g grid voltage increment. Not steady state operation, but a change. The approximate circuit for an amplifying tube is a grid voltage with the plate as a resistance and the grid voltage varying the plate resistance. You approximately get a RF high-powered variable resistor. These amplifiers are almost always operated as a voltage-coupled amplifier, especially in this application. And to do that, there's a voltage drop established between B plus and a resistor in the low-power circuits or inductance in the final circuit, where the combination of this fixed voltage drop here, or fixed resistance here, and a variable resistance here with this grid swing equals a plate voltage swing on the output. The reason that these tubes do not need to be matched is that in elementary circuit analysis, with two tubes in parallel with their plates as variable resistances, the two tubes become variable resistors in parallel, and we make the assumption that these two adjustments are ganged together. There should be a dashed line between these two. Through basic laws of circuit analysis for resistances in parallel, product over sums, those two plates are the equivalent to one variable resistor. If one's off 10%, it makes no difference, except that 1/3 of the tubes is down about 10%, and that is a trivial, meaningless amount. And we certainly don't want one of these tubes operating at 20%. that means the power output is going to be low. But this thing about one tube feeding power to the other is BS. Somebody's made it up. Violates laws of circuit analysis. The only place matched tubes matter are in push-pull, where they act as current sources, and this is oftentimes a Class B push-pull with a transformer coupling. This used to be used in tube audio circuits. Here, the currents need to match, or there's severe distortion. But even, and realize, by circuit analysis laws, in a series circuit, the current is everywhere the same. For the same drive signal to both tubes, the current must be the same in both tubes, or there'll be distortion. The drive from one tube will be less than the other, and the circuit won't be symmetrical. But even here, especially here, we never operate near idle, because operating near idle here is what results in operating in a crossover region, and that's a highly distorted area. So they bias the tubes to escape operation in a crossover region. Another thing to observe is that the careful experimenter has written with black markers 75 milliamp 5400 G sub M. We never do that to a tube. Write it on the box or write it on a slip of paper, because where that ink is will cause hot spots in the glass. So need to take that off. Another fallacy to notice here is tubes slow to warm up. There's no such thing. The filaments are heaters. They heat up in 11 seconds. And what that means is that, don't know if you can see it in the video, but these tube pins are badly oxidized. And that indicates a bad connection on the filament. Because realize these tubes have operated with these metal pins hot enough to cause severe burns on your fingers, 100, 200 degrees, and that metal oxidizes. That's necessary to take those oxides off of sandpaper, because chemicals I've found that won't touch it. And that goes a long way in preventing noise in tube circuits. Now, if you really want to do a valid test on these tubes, it's necessary to put them in a radio, because there's no reason to build a separate test fixture. The radio is ideal. Put them in, turn the grid bias control up so the tube is drawing 150 mils, and just put one tube in. This just for a static test. But put one tube in and turn the bias, actually turn the negative bias voltage down to probably about 30. So the tube is drawing 100 or 150 mils, and not in steady state. But to test it, just push the mic button and key the transmitter for an instant and read the current and release it, because otherwise the tube is going to get rather hot. 650 volts at 150 milliamp is a whole lot more dissipation than those plates can handle. That's a 17.5 watt plate, and 150 mils is 97 watts. So just do it for a brief test. But this thing of testing an idle is absolutely, totally wrong and completely unreliable. And I tested this in the rig. This is not just theory. I put in a set of good working final tubes, got full output, did this test. The idle currents varied more than 10%, but I knew better. And this is especially misleading considering the fact that there's negative feedback in the cathodes, which tends to eliminate or minimize any problems like that. So what's important here is to understand this is ham radio, this is not CB radio. We're not CBers, we're not blindly plugging tubes in. We are supposed to know these things of basic circuits. This is what ham radio is about. It is an engineering radio service, not citizens band. And if we don't understand the circuit analysis and circuit principles, we're going to be led astray by myths and fallacies like these. KBYP out.